I am here specifically to talk to you a little bit about one of the newer pieces of software that we've released at CoreOS called Flannel. So I guess just to step through a few things here, Redbeard or Brian, depending on what you're comfortable with. Customer-facing guy at CoreOS. So yes, we're CoreOS for anyone who wasn't aware. I realize you're at the meetup, but for anyone who wasn't aware, we are talking minimal Linux. Make sure that Linux Foundation stays happy. But more importantly, we are here to talk about, like we said, Flannel. So Flannel is one of the newest components of CoreOS. It is an overlay network for the actual operating system itself. It's not one of the things that directly you would run inside of a container. This is a little bit more like Fleet or etcd. And it kind of came from the idea that we wanted to have a project called twerk. But what is twerk? It is the network. Give everyone a minute to groan there. So, you know, obviously Flannel, a little bit of a better name than twerk. But why do you even need an overlay network in the first place? Everything seems to be running right now. People are spinning up containers. Everything's good to go. I would like to take one moment here before we get too far into this. Go ahead and raise your hand, Eugene. I'm going to embarrass him just for a minute. So Eugene is the powerhouse behind a lot of this. I am here just as, you know, a humble shill, if I can keep from pounding on the microphone, to talk about this a little bit. Feel free to grab me afterwards to ask questions, or if you're feeling especially good, talk to Eugene, though I'm sure he'd rather shuffle that off on me. But why do we need an overlay network? Well, we, at the moment, when it comes to containers, and when we come to the deployment story that we're talking about, a lot of us are seeking out, we're standing on the shoulders of giants, whether or not we realize it. And the folks with the Kubernetes project, so Kubernetes, aka there we go, KDs. The folks at the Kubernetes project had a vision for how they actually deployed containers at Google, how they performed the networking. And in Kubernetes, every single machine in a cluster is assigned a subnet. Now, they will assign a subnet to a cluster, and then each machine in the cluster gets assigned a portion of that subnet, which also, that being said, I'm going to take a moment just to be a little bit of a pedant. Laugh along with me here. You know, I'll let you know when it's all done. But the idea here is that, you know, most folks think of things as a class C, which is 256 IP addresses. What we're talking about for a lot of the examples here is a /24. Which is also 256 IP addresses. Now, for folks who are not, you know, into networking and just pick up stuff, the last nomenclature is called CIDR or CIDR, which stands for classless inter-domain routing. Classless, meaning no class Cs. So both may have 256 IPs, but they're not directly similar. I mean, the big takeaway there is, you know, class Cs are the state of the art in 1988. And by 1991, they had started phasing a lot of that out. So that's the end of my pedantry. And now we will get back to the actual reason that all of you came to hear, which is about our stuff and what you can do with it. So Flannel, a subnet to every machine? Yes. Yes. I mean, that's, you know, for anyone who happened to come to the meetup, I believe it was back in July or August. My memory's foggy. You may happen to remember the talk from Tim Hockin, that guy. One of his takeaways, I mean, it's a fantastic talk. There's a recording of it. You should definitely go watch it. But one of the big takeaways from it was the idea of leaving port mapping in the dust. For anybody who's using Docker today, just vanilla out of the box, they do a lot of heavy leveraging of the dynamic IANA port allocation range, which is 49,152 all the way out through 65,535. That means you can just pick one of those. They're not allocated to anybody. It's going to be safe. You know, if anybody stomps on it, well, you know, it's technically you should have looked that up in the first place to make sure that it wasn't being used. But it just means in reality that when it comes to deploy things, it makes your service discovery more complicated. Now, we have this mechanism for service discovery that we're shipping inside of the operating system. That's etcd. We do what we can to make this easier, but if all that you need is a specific IP address for a container or for an endpoint, just worry about the IP address. Getting into port mapping now means that there's additional logic and rules that you have to, you know, really kind of account for. The TLDR version of this is that having something like Flannel gives you dhcp for containers. Now, it's an oversimplification. You know, containers are already using dhcp. They're sitting behind that Docker 0 bridge. But the idea is that by having a port allocation range or a IP allocation range that you hand to each host, this, you know, /24 kind of if you use some of the default things laid out by the Kubernetes project and some of the documentation within etcd, within Flannel, sorry. It means that each container is now going to get an IP address that's visible from all of the other hosts in the cluster. Now, it gets into a little bit of weirdness because there is still NAT involved. So can you do this with a VPN? Yes, you probably could. We initially looked at some of that. But when you get into most VPN-type topologies, it's very much hub and spoke. And if you're going to start having that hub and spoke type topology, then you need to have a central arbiter for all of the communications, which comes back to a single point of failure. But Eugene's a smart guy. So one of the next things that he looked at was specifically the VPN software called Tink. It's an interesting idea because Tink introduces mesh networking to this. Now you get rid of that single point of failure, but then we're in a little bit of a boat of having to worry about the configurations sitting inside of etcd, because you want that to guarantee that all your configurations are replicated and that you don't, again, single point of failure. But the process of taking the configurations out of etcd, rendering them to files, passing them to Tink, hupping the process is suboptimal. But we were really, really hot on that one feature, which was to say the mesh network. We wanted some process for being able to ensure that you're going to be able to have two hosts running, and a container on one can talk to a container on another by a consistent IP address. So to give a little bit more to visualize this, similarly, apologize for folks way in the back, but what we've got here is we have a /8 that's been allocated to this entire CoreOS cluster. And then each host in particular has been allocated a /16. So yes, we'll pretend that it's been allocated a /16 there. So in this case, each one of these hosts is allocated a portion of that overall subnet so that none of them are actually conflicting with their IP allocations. And then from there, inside of that, each one of these containers is given a single IP address out of that allocation. Now, this is not to say that the host itself is running 10.5.0. We'll say 1 in this case, but merely that there has been a device established on the host to handle routing of that traffic. It's built into it. It's a tunnel device. It's something that allows you to get through the cluster from one host to another cleanly without worrying about what's happening in the middle, in between. We have this tunnel device. So to go into a little bit more detail here, in this case, again, we have 2 CoreOS machines. We have 4 containers running. And we have the virtual Ethernet interfaces allocated to each one of those containers with Flannel and the physical Ethernet device sitting in the middle. The idea here is that now there's a /24 allocated to each one of these containers. No. OK, yes, there is a /24 allocated to the host. And then each container is allocated an IP address as I mentioned earlier, out of that container. And we actually encapsulate the packet but going between the two hosts here to ensure that 10.1.20.2 can talk to 10.1.15.2 because the routing table for all of these machines is actually managed through a combination of Flannel and etcd. Folks following along this far? We've got a bunch of containers. Each container gets an allocated IP address. Each host has a subnet in which that container has been allocated, and each cluster has an even larger subnet that's been carved up for the individual hosts. Again, the takeaway here is that all of your containers can now directly see each other because they're not necessarily relying on the natting from the Docker process itself, but they're relying on the natting happening by Flannel. But that also speaks to that this is happening, that encapsulation there is not happening at layer 2. It's happening at layer 3. Let's just take that in for a second. It has certain allocations or ramifications. You're not going to be able to use multicast easily. You're not going to be able to just send out an ARP command and see the other containers on that network. So that means that you're not going to directly have the types of functionality that you'd expect from something like openvswitch available. Now that being said, we are working on VXlan for this. We want you to have that layer 2 type visibility, but they're non-trivial things to be fixed, problems to be solved with that, and we're actively working on them. But that raises a question here. Well, why not just use openvswitch? Well, there are a number of issues with that that we're concerned with. And the largest of which is that openvswitch really, it requires some type of control plane. If you think about openvswitch and how it's used inside of a larger project like OpenStack, where you've got Neutron routing and managing all of these networks across everything, to just directly use openvswitch would get into now writing etcd backends for openvswitch, which would only be useful to us. Shipping all of the packages, which are then going to cause the operating system itself to bloat out more and more. And it also means that we're getting into technology that only a few people really deeply understand, and we would rather keep things in the realm where we have the control to make sure that if our customers have problems, that we can very quickly react to them and very quickly solve the issues without having to broker patches being shipped upstream for a technology that goes so far beyond the scope of the very narrow problem that we're trying to solve. Now, that also touches on for some people, why didn't we just use Weave? Well, one, at the time that etcd was, Flannel, etcd, Flannel, Fleet, at the time that Flannel was actually started, when the commits first started being made on the upstream repositories, frankly put, not all of us had heard about it. But even more so, none of their open source commits were even landed on GitHub. So this became an issue of who are they? What's the deal with the code? Can we support them? Can we work with them? So, that's just touching on it. The big takeaway there is we had a problem to solve. We took the initiative to solve it. So, why is this actually important again? Why do you care about this? If you're on a cloud provider, your networking may not be predictable. Now, if you're running on Amazon, sure, you can set up a VPC, you can guarantee what all the subnets are going to be. Things may play a little bit nicely. But for folks who were listening to me jabberjaw a few months ago, the idea that we're doing with the goal of CoreOS is to give you a similar experience regardless of the cloud platform that you're deploying on. And that's not necessarily trivial to complete. But by having an overlay network, you can begin to guarantee that your containers bind predictably to known ports. Now you don't have to worry about how you are going to route all of the traffic between containers that may be a part of the same application but residing on different hosts. If I deploy 100 containers across 24 hosts, I can now rest assured that they're going to be able to talk to each other via a common mechanism, and that's Flannel. So I apologize greatly for the very abbreviated talk, but does anyone have questions about this? Yes?
This might be super naive, but is there a performance cost to encapsulating those packets?
Yes, there is a slight performance cost. We actually, in the very first blog post that we had talking about Flannel, we actually published some of those metrics because it was one of the main things that we were concerned about with that. What was it, about like 3%?
It was, well, for latency was severe. It was about 50%, well, twice as slow for latency. But for bandwidth, which is probably what you care about a little bit more, it was like maybe sub 10%. It was not very noticeable.
Yeah. Now, one of the other things that's important to point out is that this is still designed to be used within a single cloud environment. Because if you were to really map it out and think about it, if I had an environment running on Google Compute and I had another environment running on Rackspace, there's already one level of NAT occurring because they abstract your public IPs from the private IPs that are actually assigned to a host. And then to have another layer of NAT on there means that if I wanted to route containers running on one host all the way across the public internet to a secondary host running on a different cloud provider, that double NAT is really going to confuse things. It also introduces another point, though, is that with this, because of the concerns around performance, and because we were really looking at the idea of you're already going to be running on a single cloud provider, ideally, you're going to have a strong view of that traffic. There is no direct encryption that's happening over that as well. You could always stick it inside of something like an IPsec tunnel, but it's really just focused right now on the getting things done aspect of it. That being said, we are worried about that. I personally am constantly paranoid about my traffic being man in the middle. So the takeaway there is rest assured that it's things that we are considering and that we really are worried about to one extent or another. But there's a definite wheelhouse of, first and foremost, make sure that it works and that the technology is going to be sound before really putting all the features into it. And then you, sir, had a question. Yes?
Yeah, so I was curious, how often does Flannel D synchronize its routing information with HacDC?
How often?
So HacDC has a concept of a watch where you can do a long haul, HTTP long haul, so it places that, and then as soon as information arrives in HacDC, all the watches get notified, so propagation delay basically of the CD, which is millisecond or subsecond.
Okay. We're going to take one or two more questions and then kind of wrap it up here. The one thing that I was going to say, though, also is that when Jesse mentioned in the previous talk one of the problems of doing port mapping, it really hits home that this is one of the problems that we're actually trying to solve here. To make it so that you don't have to discover the port that a single container is running and handle that NAT mapping between two different instances. Like if you've got web containers, you know that they're going to be running on 80 or 443. The protocol is built into that. If you're running something like Cassandra, where there's a gossip protocol involved, and they never really considered running that over a NATed or a port mapped infrastructure, it makes it a lot easier to deploy those types of things. One more question? I ask you right in the front.
So you were basically encapsulating the packet,
yep,
and shipping it out over the backlink and back into the other machines. What container are you using? Because 3% suggests about 1,500.
So again, I will.
I'm just wondering, are you using a big MTU or just like little link?
Well, you'll end up using the MTU, the one which you're running on. So Amazon actually runs Jumper frames, so MTU by
whatever it needs to.
by the overhead. And,
But obviously, the frame itself is bigger, then you have that much less overhead.
yeah. But if you're running, but it's not something that's under our control.
Of course.
Now, from the performance implication for, say, openvswitch or layer 2, top of rack switch, where you tromp one up and then you have to do between subnet, software client routing, it seems as though your implementation is actually much cleaner because it's any effectively routing, right, within the subnet, right? So rather than having to, instead of having the layer 2 meshing where you see the vSwitch, where they still require software client router, and they're in between virtual machines, it seems like you're any routing within the subnet. So is it not more performant than the other alternative, or?
Well, openvswitch will run on the kernel. It's the advantage of the kernel, so we have that advantage, although we are going to take advantage of the complete advantage as well. In some sense, it's very similar to openvswitch. I mean, we have layer 2, we have layer 3, and we do have a router as the Flannel team access the router. So that's not similar, but there is not like a centralized router that they have.
Awesome. Well, thank you much, and we're going to give it a few minutes here for folks to talk and mill about, and then following, we'll have Brandon with a little bit more information about where etcd has been going.